This video is going to be kind of on the long side because in class we'll take section 1.2 and break it down into 2 days. The first day we're going to focus on linear measures, so just distance along a line segment. And then the second day we're going to take that line segment, we're going to put it on a graph, and we're going to find the distance between two endpoints on a coordinate plane. So feel free to jump around in this video. If you just need help with the distance formula, go ahead and jump to the second half. So in these first couple examples, we are looking at linear measure. We're trying to find the length of each indicated segment. It looks like on the left, I'm finding the length of segment AB. That means I want to find the distance between point A and point B. We've just got some subtraction to do. If the entire segment is 100 centimeters and BC is 85 centimeters, the remaining chunk is just going to be 15 centimeters. And I found that just by taking 100 minus 85. All right, the one on the right is just a little more complicated. Here I'm finding WY. So I want to find the distance between W and Y. Notice it's labeled as 3x. A lot of people just want to give me 3x as an answer. It's not that easy because we need to know the length. Length can't have a variable in it. It has to be a number. So I know that the two sections, segment XW and segment WY, put together make up the whole segment XY. So we're going to write that out in an equation. XW plus WY equals XY. And then we're going to do some substitution. Most of you will probably skip this first step and jump right to 6x plus 3x equals 81. We can combine like terms. 9x equals 81. We can divide by 9 on each side. X equals 9. And we're not quite done because I wanted to find the length of WY. Well, WY is 3x. So 3 times 9 would be 18 centimeters. The next chunk of problems are really easy if you can understand what the directions are saying. I have to find ST and find WU. Whenever you see two capital letters next to each other without a symbol over the top, like a line segment or a ray, it's just telling you to find the distance between those two things. So when it says find ST, it's asking what's the difference between point S and point T. It looks like this number line is just counting by ones, so that would be a distance of 3 units. And then WU, again, same idea. I'm looking for the distance between point W and point U. Well, U is at -2, W is at 5, so that would be a distance of 7. All right, congruent. That is a word we will see a whole bunch in geometry. Congruent things are just things that have the same measure. So in this case, we're talking about congruent segments, but there'll be many things in this class that end up being congruent. And again, that just means if I were to measure them, if I were to take a ruler to these two segments, they would be exactly the same. So in the picture on the screen, segment AB is congruent to segment CD. We've got a symbol for congruent, and it's just the equal sign with a squiggle over the top. You can see it right here. That symbol means congruent to. So in our next two examples, we're asked to identify any congruent segments. So again, we're asked to identify anything where if I were to measure it, it would have the same length. In this parallelogram on the left, I see that AD and BC are both 11 centimeters. And we can identify congruence just by making those little slashes that I did to show that those two segments are the same. We can also identify congruence by writing a congruency statement. So I could say segment AD is congruent to segment BC. And then if you look on the other sides of that parallelogram, AB and DC are both 5 centimeters. I can't denote it with a slash like I did for AD and BC because then it would say that every single side is the same, which it's not. So instead, I'm going to add 2 of those slashes. That shows that it's different from AD and BC, but AB and DC are congruent. Let's write that out in a congruency statement. AB is congruent to DC. In the figure on the right, I have 2 segments that are already identified as congruent. AD and BC are marked with that congruency slash. So for my statement, I would say segment AD is congruent to segment BC. And that's all I can write for that one because the other 2 sides are different lengths. All right, so that's linear measure and congruency. The second topic that came with section 1.2 is the distance formula, or distance between 2 points. So you see this big crazy formula up at the top where PQ is the square root of x2 minus x1 squared plus y2 minus y1 squared. In that formula, we've got variables to plug in, x2, x1, y2, and y1. Those come from the 2 points that we're finding the distance between. So in this case, P would be at point x1, y1, and Q would be at point x2, y2. I don't usually actually use this distance formula in this form. I just kind of think about what's going on, but I'm going to show a couple of different examples so you can see it with plugging and chugging in the formula and with the shortcut that I'll show you in the second example. So I want to find the distance between these 2 points, 2, 3, and negative 5, 0. With the distance formula, 2, 3 would be like x1, y1, and negative 5, 0 would be like my x2, y2. So now I can just take those things and plug them into my equation. And I usually say lowercase d for distance rather than the PQ they used for those points. So d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And then let's just plug in what we know. So this x2 is negative 5. x1 is 2. y2 is 0. y1 is 3. Remember to follow your order of operations, so start with what's in parentheses. We're going to leave the square root alone for now. Negative 5 minus 2 is going to become a negative 7 squared. 0 minus 3 is going to become a negative 3, and that's squared. We'll bring this up here and we'll simplify a little bit. Negative 7 squared would mean negative 7 times negative 7, that's 49. Negative 3 squared would mean negative 3 times negative 3, that's a positive 9. 49 plus 9 is 58. So the distance between these 2 points is the square root of 58. If we were asked to find a decimal approximation, I could throw that in a calculator, and that is about 7.6 units. And either of those answers would be okay. All right, so that's the distance formula. Again, I've got a couple more examples, and I'm going to show you a slightly different method that is actually very similar. So actually, let's go back and look at the distance formula. There are kind of 3 operations that we do in the distance formula. The first thing we do is we find the distance, how far x travels and how far y travels. So when we look at this x2 minus x1, that's telling me how long is this line. And then when we find y2 minus y1, that tells me how long is this line. Then once we have those 2 line lengths, we square them, we add them together, and we take the square root, which actually comes from the Pythagorean theorem. So rather than using the formula, I'm just going to follow those steps. I'm going to find the distance x travels. I'm going to find the distance y travels. Then I'll square them, add them together, and take the square root. So my x's travel from negative 7 to 2. Negative 7 to 2 is going to be a change of 9 units. My y's travel from 2 to 6. 2 to 6 is going to be a change of 4 units. Now that I have those 2 numbers, I'm going to square them. I'm just going to slide this 9 down a little bit so they line up. I'm going to add them together, and then I'll take the square root. So 9 squared is 81. 4 squared is 16. 81 plus 16 is 97. So my answer would be the square root of 97, which is approximately 9.85. So that's an alternative to the distance formula. In reality, I did the same thing in both of those examples. I just framed it a little bit differently in my mind. And then this last one, I think I'll actually do it both ways so we can see that they'll give us the exact same answer. So over on the left, let's try out our distance formula again. The square root of x2 minus x1 squared plus y2 minus y1 squared. Plug in our numbers. I'm going to say 4 comma 5 is going to be my x1, y1, and negative 2, negative 3 is going to be my x2, y2. So that would make x2 a negative 2. x1 would be a positive 4. y2 would be a negative 3. y1 would be a positive 5. We're going to follow order of operations when we evaluate this. So start with your parentheses. Negative 2 minus 4 is going to be negative 6. Negative 3 minus 5 is going to be negative 8. Negative 6 squared would mean negative 6 times negative 6. That would be a positive 36. Negative 8 squared would be negative 8 times negative 8. That would be a positive 64. Square root of 100 is 10. And on this one, you know the square root of 100 is 10. Don't leave it in a square root. If it simplifies to a whole number, we should always simplify it. All right, now I'm going to do this exact same problem using my distance formula shortcut and show you that we do the same thing. So first thing I'm going to do is figure out how much x changes and how much y changes. So let's write our points over here. We go from 4, 5 to negative 2, negative 3. All right, from 4 to negative 2, I decrease 6. I'm going to leave it as a positive 6 because we're going to square it anyway. But if you had negative 6, it's going to work out just fine. From 5 to negative 3, I decrease 8. Same thing. I'll make it a positive 8 because we're just going to square it anyway. And then once I have those changes, I'm going to square them, add them together, and then I'll take the square root. So 6 squared is 36. 8 squared is 64. That would become the square root of 100, which would be 10. So either way, I'm doing the exact same process. It's just the distance formula. There are a lot of variables, and that can be kind of scary sometimes. So usually I prefer to just break it down and look at the steps individually. So you figure out how much x changes, how much y changes, and then square those two numbers, add them together, and take the square root.